So we move on to a fundamental theorem of calculus. It's one of the most important theorems in calculus. Mostly it deals with integrals. And the key here is suppose f of x is a positive function and by positive function I mean f of x is greater than 0 for a less than x less than equal to b on some interval. Then we know f of integral a to b f of x dx is the area under the curve. So, for instance, if I have So if I pick A and B, then the area under the curve, which would be all of this, all of it here, would form the integral a to b f of x dx. That's great. Now I'm going to copy this. So the same function, but what I'm going to do now, I'm going to pick an arbitrary line between A and B, and I'm going to call it T. So imagine if I move this T between A and B, then the area will change with respect to T. Now that is a given, it should be obvious, and I'll draw a couple of images to demonstrate this. So if T is right over there, then the area would be all of that. And if I move that T a bit, And let's say I drew it over here. Then the area under the curve would be that pi. So we know that the integral is a real number. It would also imply, because it is the area under the curve, we also know that the area I have here and the area I have there A1 and A2 are also real numbers. The only difference here is that the value changes with respect to t. Perhaps I could use a different letter to avoid confusion. I'm going to call that some arbitrary value x. So as I move that x, the area is going to change. So if x is x1 there, then this area would simply be integral a to x1 f of some t dt. That t is what we call a dummy variable. So x is x1. If I pick x is equal to x2, then this area, a2, would be integral a to x2 f of t dt. And from the figures, you can see that the area A1 is greater than A2. You can see that clearly. A1 is bigger than A2. So what does the first fundamental theorem of calculus state? Now, if I keep on moving this line, the red line and the purple line, back and forth, I'm going to get different values for the area. So the fundamental theorem of calculus, I would say this is rule 1, states that g of x is equal to integral a to x, the dummy variable t, dt. And g of x is a continuous function. As an example, I can relate this to what I used up there. So here, if I plug in g of x1, that would equal to the area A1, and g of x2 would equal to the area A2. So I could pick any x, and I could come up with a continuous function that represents the area under the curve. So that is the first fundamental theorem of calculus. You could call it FTC 1. Now, there is a close relationship between this area and the derivative, and which is one of the reasons we call it the antiderivative. So what is an antiderivative and how can we visualize this? suppose we have a function and let's say I have a curve of that sort between A and B, and I'm going to pick two lines and those two lines are x and x plus h, and of course I would end up having f of x and f of x plus h. And that right there is an area, which we know. And the distance between x and x plus h is simply h. And that point right there is f of x. And that point right there is f of x plus h. And keep in mind, we can find that area either using the left endpoint or the right endpoint. So, using the definition from FTC1, Fundamental of Theorem of Calculus 1, I could write g of x plus h as integral a to x plus h f of t dt. T is just the dummy variable. And g of x as a to x f of t dt, that is also a dummy variable. Now, if I subtract the two, g of x plus h minus g of x, that would simply be integral a to x plus h f of t dt minus integral a to x f of t dt. Now, I could also write this using one of the properties of definite integrals. The area all the way up to x plus h is simply, perhaps I should copy this. So I can rewrite the area up to x plus h as this. So the area from a to x and the area from x to x plus h. So if I call this A1 and if I call that A2, the area from A to x plus h is simply A1 plus A2. And then I have the third term minus integral a to x f of t dt. So, what is A1? A1 is integral a to x f of t dt. A2 is integral x to x plus h f of t dt minus integral a to x f of t dt. The first and the last terms would get cancelled. I'd simply have integral x to x plus h f of t dt. Now that is simply the area under the curve A2, because we are simply looking from x all the way up to x plus h. So that is simply A2. But if we use the rectangle, approximation rectangle, that is simply equal to h times f of x. I'm using the left endpoint. So what we have shown is g of x plus h minus g of x is approximately equal to h times f of x. This would imply g of x plus h minus g of x divided by h would be approximately equal to f of x, which would mean limit h approaches 0, g of x plus h minus g of x divided by h would be approximately equal to f of x, but in limit it would simply be equal to f of x. But the left-hand side, by definition of derivative, the left-hand side is simply the derivative of g of x. So g prime of x would equal to f of x. Hence, g of x is called the antiderivative. So now you could see the relationship between the antiderivative and the derivative, the integral. So another way to write it, we know that g of x integral a to x f of t dt, d over dx of g of x is simply g prime of x, would equal d over dx of integral a to x f of t dt, and that would equal f of x from our previous argument right over here. So we could infer it this way also, and this is what we call the Leibniz notation. But all we are trying to say is the derivative of g of x, which is the integral, would equal to the function f of x, and they are called the antiderivatives. An indefinite integral is one without any limits. In the sense, we simply have integral f of x dx that will result in an antiderivative plus c. Now this is what we call a constant of integration. Now, you may ask me why we should put that c. I'll take a simple example. Integral x squared dx. So the antiderivative must be something. So yes, if you differentiate the uppercase f of x, you would end up getting the lowercase f of x. So the uppercase f of x in this case is x cubed over 3. Now if I differentiate this, I end up getting 3x squared over 3. 3's would go away. I get x squared. Now, all we know is if we differentiate x cubed over 3, I get x squared. But what are other possible answers? I could have x cubed over 3 plus 2. I could have x cubed over 3 minus 2. Differentiate both of them. You get 3x squared over 3. Derivative of 2 is 0. Again, 3x squared over 3. Derivative of minus 2 is 0. Both of them would give us x squared. So if I picked x cubed over 3 as an antiderivative, I'm going to get x squared. If I took x cubed over 3 minus 2 and I found the answer by differentiation, I will get x squared. If I picked simply x cubed over 3, I would get x squared. So which is it? All of these are possible answers. So that is a antiderivative, that is an antiderivative, that is also an antiderivative. So which is it? We do not know. And that is why we put the constant of integration there. But how do we solve for that constant of integration? So if we know some condition about f of x, for example, f of x is equal, f of 0 equals 1, then we will have a unique answer for the indefinite integral, i.e., there will be no constant of integration. So if I impose a condition on f of x, then I won't have the constant of integration. Now this table here is very important. If you plan on going to upper level mathematics, this table is only get lengthier. So key things to note is if we have a constant multiplied to f of x, we can pull the constant out, then take the integral. If I have two functions in sum, I can separate the integrals out and integrate them separately. We have seen this before. If we integrate dx, k times dx, I can pull the constant out and write it as k times integral dx plus c. Integral of dx is always x, so the answer would be kx plus c. The rest of the integrals, they are things that you've got to know. You don't have to memorize them. You could simply keep your table with you and you make use of the table to get to the answer. So the book has multiple other indefinite integrals summarized, so you can use them as a reference. So in every single one of these cases, let me take sine x dx for instance. If I took the derivative of negative cosine x, I will get sine x. If I took the derivative of sine x, I will get cosine x. If I took the derivative of e raised x plus c, I will get e raised x. Every time I take the derivative, that constant will disappear. But do not forget to put the constant when we have indefinite integrals. So here is our first indefinite integral, and we want to integrate this. So the first step is to write it in a form that we can integrate. So I'm going to remove the radical and write it as x raised 5 raised 1 over 4 dx. And that would give us x raised 5 over 4 dx. If we go back and look at the table, we have that x raised n is simply x raised n plus 1 divided by n plus 1 plus c. However, n cannot be equal to negative 1. If it is negative 1, the definite integral is ln of absolute value of x plus c. Fortunately for us, n is not negative 1. It is 5 over 4 Recall integral of x raised n dx is x raised n plus 1 over n plus 1 plus c. Since n is 5 over 4, integral square root of x raised 5, or fourth root, is simply x raised 5 over 4 plus 1 divided by 5 over 4 plus 1 plus c. If we take the common denominator and simplify, we have 9 over 4 divided by 9 over 4 plus c. That would be 4 over 9, x raised 9 over 4 plus c. I want you to try at home. If you differentiate uppercase f of x equals 4 over 9, x raised 9 over 4 plus c, you will get lowercase f of x, which simply is x raised 5 over 4, or the fourth root of x raised 5. Try that at home, and you can reinforce the concept that the antiderivative, when differentiated, it is going to give the function that is inside the integral. We have a fancy name for it. It is called the integrand. So here we have an indefinite integral in terms of u, and we have a bunch of terms added and subtracted. We know that we can split the integral and write it as individual integrals as long as things are in additions or subtractions. So u raised 6 du minus integral 2 u raised 5 du minus integral u cubed du plus integral 2 over 7 du. N here is 6. N there is 5. N there is 3. And I can pull the constant out. So recall integral of dx is simply x plus c. Likewise, integral of du is simply u plus c. An easier way to remember this is the integral and the derivative would sort of go away, leaving you with u. Now that is a very informal way of remembering this, but it is helpful when you try to learn integrals. So using the previous identity, the first integral would reduce to e raised 6 plus 1 over 6 plus 1 minus 2 u raised 5 plus 1 over 5 plus 1 minus u raised 3 plus 1 over 3 plus 1 plus 2 over 7u, which will give us u raised 7 or plus c over 7 minus u raised 6 over 6 times 2 minus u raised 4 over 4 plus 2 over 7 u plus c. You may ask me, well, shouldn't we put a constant for each of the integrals? Not necessary. If you have a constant for each of the integrals, if you add them together, you would end up getting a constant at the end. So I tell students that you can just integrate the indefinite integral properly and throw in the constant at the very last step. So that is perfectly fine. As long as you put a constant at the very last step when you write the answer, we're okay. So here is an indefinite integral where we have two functions in the integrand that are in product. Now we can't simply write it as now this is incorrect. You can only split the integral if you have sums or differences. We don't have that, we have product. So let's change the integrand into something with sums and differences. So I could rewrite this as integral, if I FOIL, 2u squared plus u plus 8u plus 4 integral 2u squared plus 9u plus 4 du. Now I have sums of terms, so I could split the integral and write it as 2u squared du plus 9u du plus 4 du. I could pull the constants out. 2 integral u squared du plus 9 integral u du plus 4 integral du. N here is 2. N there is 1. There is no n, so here it's 2 times u raised 2 plus 1 over 2 plus 1. 9 times u raised 1 plus 1 over 1 plus 1. 4 times integral du is u. So we have 2u cubed over 3 plus 9u squared over 2 plus 4u plus c. You can see that I saved that constant of integration till the very last step, and I just threw it in at the very last step.